Hello everyone, my name is Lu. I will present our paper, Leveraging RAG and the Generative AI for Enhanced Healthcare Navigation and Information Access in Intelligent Wheelchair System. RAG is Retrieval Augmented Generation. Here is the outline. There are four parts in the presentation. The first part is introduction and problem definition. Next, we will introduce the technical system design. And the next is system implementation. Finally, we will discuss about validation and impact in our research. Now, we will talk about introduction and the problem definition about our paper. Nowadays, we face the healthcare accessibility challenges. The critical statistics shows that 60% of global population consists of people with disabilities. In addition, Taiwan enters a super-aged society. Besides, 13.2% growth in disabled population over past decade. Furthermore, 7.4% compound annual growth rate in wheelchair market. The core problems are such that registration barriers, information access, navigation difficulties, emergency response, and communication barriers. There are some current limitations. Isolated technology solutions rather than integrated systems. Limited focus on comprehensive disability-specific needs. In addition, few systems combining multi-model iterations. Furthermore, lack of seamless hospital navigation solutions. Therefore, we propose the paper. Here are our contributions. Integrated AI IoT platform, multi-model iteration, and we have wheelchair optimized navigation. We use enhanced A-star algorithm for accessibility. Furthermore, real-time health iteration in our system. We have continuous monitoring with family alerts. Next, we discuss our second part, technical system design. Here is the system or architecture overview about our paper, Intelligent Hospital Wheelchair System Architecture Overview. There are three-tier decentralized architecture, AI Care Wheelchair Kit, Cloud Server Infrastructure, and mobile app ecosystems. There are some parts, some AI Care Wheelchair Kit in it. They use it for main processing, wireless communication, automated check-in, and the route visualization. In the cloud server infrastructure, they also have four parts. We use Raspberry Pi Edge Gateway and QTT Hub, large language model integration, data management and storage, and also use the line WebSocket for family alerts. AQTT is message queuing telemetry transport. In another part, mobile app ecosystem, we also have four components. Hospital information system interface, patient care system monitoring, Face ID authentication, and family communication portal. Here are the hardware components. In the core system component, there are three parts: processing display, sensing module, and communication protocols. In processing display, RISC-V chip co-development board, our dual-band Wi-Fi Bluetooth BLE, our energy-efficient route display used for that. In sensing modules, we have RFID for health insurance card simulation, our pulse sensor for continuous heart rate monitoring, or use the ESF for contactless infrared temperature sensing. For the communication protocols, the MQTT for IoT messaging, Wi-Fi for wireless connectivity, stereo communication for local control, and API interfaces for app integration. The wheelchair optimized pathfinding, we propose the enhanced A-star algorithms. Fn is equal to Gn plus Hn plus lambda Cn. The rig enhanced information tree-view, it shows that context-aware medical query processing, natural language route descriptions, real-time hospital information access, and multi-language support by whisper iteration. The e-paper display process are as follows. The first is mobile request, then database retrieval, and the next is AD support calculation, and the next is generated artificial intelligence test conversion. Finally is e-paper display. Now we will show the system implementation in our research. The study used automated registration and check-in. We use RFID-based patient registration. There are 5 processes below, and we have 4 benefits. For example, eliminate waiting queues, reduces physical strain on patients, increases patient autonomy, streamlines hospital workflow. In the AI voice integration system, there we use the multiple language communication support. The voice processing pipeline has 5 stages and key features such as real-time Chinese translation for foreign patients, natural language medical query processing, voice control wheelchair functions, and emergency voice commands. In the physiological monitoring and alert, this is a continuous health monitoring. The monitoring process has 5 stages: sensor initialization, data calculation, database storage, real-time analysis, and family alerts. There are 5 safety features: continuous vital sign monitoring, automatic emergency detection, family notification system, healthcare staff alerts, and historical data tracking. The clinical integration in electronic health record system connectivity, personalized care recommendation, and medication reminder iteration. The mobile app and the family interaction is a comprehensive patient support ecosystem. The hospital step interface has real-time patient check-in status, wheelchair sensor data monitoring, patient information access, emergency alert management, and for patient features as has have physiological data visualization, AI-powered route guidance, voice interaction controls, and monitor medical appointment scheduling. The family support systems can use like robot and real-time health status alert, hospital information access, communication with healthcare team. Finally, we will introduce the validation and the impact about our research. The security and privacy considerations in healthcare data detection framework, data privacy measures, and communication security, system integrity, and operational robustness is considered in the proposed research. Here is the evaluation results and the user interface. The system performance and the user experience, the implementation achievements are successful integrated all hardware components, MQTT communication between wheelchair and the cloud, the real-time health monitoring functionality, e-paper route display operational. The user interface features has 4 features: patient dashboard, AI map function, hospital interaction, and family line bot. The quantitative benefit, for example, reduce registration time through RFID automation, improve the information visualization by e-paper display, enhance the medical experience for patients and families, streamlined hospital operational efficiency. The study has comprehensive healthcare improvement for healthcare personnel, for patients with disabilities, or for healthcare institutions. However, there are some current challenges and research directions. For system limitations and future research directions, for example, advanced obstacle detections using computer vision or enhanced AI-driven predictive health analysis. And there are some scalability potential, for example, integration with national health databases. In conclusion, the proposed research has 4 key achievements: developed integration AI IoT wheelchair system addressing multiple disability, demonstrative successful RAG and generative AI integration in healthcare, created a comprehensive patient support ecosystem, and established the foundation for accessible smart hospital infrastructure. There are some clinical significance, addresses 16% of global population with disabilities, supports aging population healthcare needs, enhances healthcare accessibility and patient autonomy, reduces barriers to medical care access. And thank you for your listening.